Hi everyone, I'm Cheryl. In this problem, we're going to be using a double integral using polar coordinates to find the volume of a solid created by z equals xy and also bounded by the circle x squared plus y squared equals 1 that's in the first octant. So I've already drawn a little picture here of the region over which I'll be integrating. So here's that circle of radius 1 that would be in the first octant. However, I want to change everything into polar coordinates. So let's begin by getting a formula for my volume. We know that to find the volume, I'll be taking the double integral over a region of f of xy dA. In this particular problem, that will be the double integral over my region of x times y dA. Now, this is not using polar coordinates. So the next thing I want to do is shift my focus so that I'm working in polar coordinates. Now, in order to do that, I know that x is the same thing as r cosine theta and y is the same thing as r sine theta. So I can rewrite this as r cosine theta, r sine theta. And the dA, if I'm going to write it in polar coordinates, is going to be r dr d theta. So now I have the integrand set up, but I have to worry about these limits of integration. So let's go back to that picture that I had. Instead of using either a horizontal or a vertical representative element, I'm going to be using an R-simple technique. So the R values are going to be going from 0 out to 1 because my circle has radius 1. So those inside limits of integration will be from 0 to 1. And then as I build up all these representative elements, I'll be going from angle 0 to pi over 2. So my outside limits of integration will be from 0 to pi divided by 2. All right, my integral is now set up. I think I'm going to do a little simplification before I dive into the integration though. So let's see what I have. The integral from 0 to pi over 2, integral 0 to 1. This piece can be simplified into r cubed cosine theta sine theta dr d theta. Okay, so now I'm going to work on that inside integral first. The variable of integration is r, which means I'm going to treat theta as if it's a constant. So that means that the cosine theta times the sine of theta can be thought of as a constant. So I'll have the integral from 0 to pi over 2 of r to the 4th over 4 times cosine theta sine theta, evaluated from 0 to 1, and I still have my d theta. All right. The next thing I need to do then is to plug in my upper and lower limits of integration. So I have the integral still from 0 to pi over 2. I haven't touched that outside integral yet. Plugging into 1 for the r values. I'll have 1/4 cosine theta sine theta. So that's 1/4 cosine theta sine theta. Then I have to subtract what happens when I plug a 0 in for the r. But when I plug 0 in for r, that's going to make that entire term 0. So that piece goes away, and I'm just left with the 1/4 cosine theta sine theta d theta. All right, so now I'm ready to finally get to that outside integral. All right, so to do this, I'm going to need a little u substitution. It's simple enough, I think we can do this without writing out the details. The 1/4 is going to be the constant that pulls out. And when I integrate cosine theta sine theta, if I were to let u equal sine theta, I'm going to end up with sine squared theta all over 2, evaluated from 0 to pi over 2. All right, now it's time to plug in my upper and lower limits. So I'll have 1/8 times the sine of pi over 2 squared, and then I'll subtract what happens when I plug in a 0, which will be 1/8 times the sine of 0 squared. Well, the sine of pi over 2 is 1, and 1 squared is 1. So that first term just gives me a 1/8. The sine of 0 is 0, which knocks out that entire term, and my final result is 1/8. And again, this is a volume, so 1/8 cubic units. I hope that was helpful. Thanks.